Welcome everyone. Thanks for joining us today. Some of you will know that ACES is a national centre of excellence for electromaterial science, and we're charged with the discovery and development of new electromaterials and the use of advanced fabrication tools, which we often develop in-house in order to integrate those discoveries into structures and into devices, and particularly for use in energy and in health. Our technology showcase events, and we have 6 of them. We're about halfway through. These events are set up to highlight a number of discoveries that we believe have the potential for commercialization and practical application. We're also very aware within ACES that those advances are best progressed through forming partnerships with others with complementary skills. And so that's what we're keen to do by hosting this series of webinars on our ACES technology showcase. So the theme today is to have a look at what we're doing in the electrochemical reduction of carbon dioxide. That falls in our synthetic energy systems theme within the Centre of Excellence, and that's led by Professor Doug McFarlane, and I'll hand over to Doug.
Thanks, Gordon. So just to more deeply introduce this topic this afternoon to everybody, and our history in it in the centre. We for many years had a lot of activity in water splitting as a way of using renewable energy to transform that energy, so to speak, into some sort of energy carrier, which in the water splitting case is hydrogen. And in the first era of the centre, that produced a spin-out company, Aquahydrix, which led the commercialization of the ACES technology in that area. So moving on from that, in the second era of the centre, we decided to focus on other similar, because they are all very similar, reduction reactions using renewable energy, or essentially renewable electrons, to reduce things, and focused initially on carbon dioxide as an important potential substrate, and then more laterally we've focused on nitrogen to ammonia as an important energy carrying transformation. So with carbon dioxide, the concept here is that if you can use carbon dioxide as a feedstock, apply renewable energy to it, the reduction reaction then can produce a series of reduced carbon compounds, in principle all the way, and there's a lot of electrons involved in all the way, so to speak, to hydrocarbons. And we'll see a bit more about that speciation of the carbon materials in a moment from the others. So the idea there is that in a cell, an electrochemical cell that in some respects looks a little bit like a water splitting cell, we have water oxidation on one side, and we have carbon dioxide reduction on the other side, and producing this suite of products depending on the catalyst that's on that carbon dioxide reducing electrode. And if the source of that carbon dioxide then is for example a point source like a power station, or very interestingly cement production, then the carbon dioxide, or the carbon effectively, can be considered to be the energy carrier in a closed loop that is passing through the atmosphere as the return part of the loop, so to speak. And in an era in the future where perhaps via a carbon tax that there's a momentum towards carbon capture, then one of the things one could do with that carbon and this technology is to then completely close the loop so that you can recycle that carbon into the renewable fuel once again, and around it goes that carbon neutral cycle. So as I say, there's a number of or several parts of that technology, and this is very much about the reduction side of the technology, where the energy is introduced and the material or the liquid fuel that's produced from that then is produced in that process. So I'm going to hand over then to tell you a bit more about the detail of these reactions to our clever young researchers in the centre. We've got people both at Wollongong and at Monash researching this. And first up, we've got Dr. Kaiyun Wang, who's a senior postdoctoral fellow in the centre, and she'll tell you a bit about what she's been doing.
Yeah, just for carbon dioxide, I already said carbon dioxide is a greenhouse, but also is an energy carrier. For the carbon dioxide is a very important carbon source. And, you can see from here, that for carbon dioxide, utilizing products has a huge market. That is, price is about $5 trillion US dollars. And to deploy the electroreduction technology into the industry scale, and it has to be produce the products in a more sustainable manner. It's compared to that conventional produce method in terms of economic benefits, in addition to that environmental benefits. So this here is that to show that tackle economic analysis. And the red spot is that current market price based on in 2017. And that is black spots is calculated based on that minimum electricity required. This also means this happens in that reverse potential. And also that the electricity price is lower, is about 5 US cents. We can see here, use this technology that to produce the some products like carbon monoxide and the formic acid and this ethane. That is price much lower than current price. This means that it has high potential profit margin. And for that, carbon monoxide is a very strong reduction agent. It will be extensively used in that metal manufacture and also produce a variety of chemicals. And for the carbon monoxide, there is a steady market. That growth is over the 5 years from 2017 to 2023. That is at a growth rate of that 1.9, and that rate is the CAGR, the compound annual growth rate ratio. And for carbon dioxide, when we produce, when carbon dioxide reduce, also some happens is that produce the hydrogen. And when combined with hydrogen, carbon monoxide at a specific ratio, we call the synthetic gas. For the synthetic gas, it can be used directly in the field, and also it can be used directly with the starting material without separation, can use it in the facial structure reaction. For this one, that growth rate, growth rate is very high, is over 10%. And over the next 5 years. And for another product, popular product is formic acid or formic. This is a liquid, and this is very easy to be stored and distribute, and according to the current, infrastructures. For the formic, currently mainly used as, preserves or that, antibiotic, that agents in the livestock feed. And another is very important and emerging that application of formic acid. It is a strong that media for hydrogen storage. And this is that growth is or next 5 years about 1.3. And some basic information of carbon dioxide reduction. For the carbon dioxide, that I already said is multiple, multiple electron proton transfer. You can see here from carbon dioxide, we can get different products and is involved and multiple electrons and let's say is protons. And so this also means this is the post-selectivity related with the scanning relation. And this means, for carbon dioxide itself is a linear, stable molecule, is thermodynamic stable. it needs a lot of energy to activate it. You can see here is very high potential need applied to activate it. And these reactions, we also, we can, see that after the activation and to produce that carbon products, that potential is very similar with the hydrogen evolution. This means that it's not just sluggish, you need a high energy to activate the carbon dioxide molecule, or that has competitive hydrogen evolution reaction. Yeah, and during performance, when we do the testing in the electrical performance, it react as the problem react as high over potential, low selectivity, and low current density. And for carbon dioxide reduction program, we have our research areas has covered nearly all the aspects that impact on the electrical performance. Firstly, is from that is catalyst. We are developing low-cost catalyst, and this allowing that fast occurring of a target reduction reaction with high selectivity. It also means that product in high purity and activity and this high current. And also it's, we are developing the gas diffusion electrode. This aim to overcome the mass transport limitation of carbon dioxide. Carbon dioxide have a low solubility in the electrolyte. Also, we are just, developing the prototype scalable reactors for industrial applications. Currently, we just starting a new direction is concurrent electroreduction and storage carbon dioxide for the use of seawater. And you see what as electrolyte to electroreduce the carbon dioxide, and also the divalent salts and the ions like the calcium or magnesium can react with the carbon dioxide and produce some carbonates. And to date, we have make understanding outcomes, and it's international our understanding outcomes has been recognized internationally. Over 50 peer-reviewed journals have been published, and the most of these articles in the Q1 journals in the research area of material science, energy, and electrochemistry, including these research journals, like in energy, environmental science, and quantity semi, advanced energy material, and ACES energy letters. And for the catalyst development strategies, first we want to try to make fully use of the materials. The first strategy is downsizing, and this is nano-structuralizing or automatic structuralizing. And this is increasing activity size. It make most use of the electromaterial. Also, we all know when the material downsized to a nano scale or automatic scale, the inherent property will change. We also change the inherent activity for high energy energy. Yeah, for the downsizing, this is the second strategy we're using is the surface engineering. We already know, the carbon dioxide is interfacial reaction, and the interface properties play an important role in all the steps. And this we try to is breaking the scaling reaction and increasing the intrinsic activity for high selectivity. For the catalyst, we have developed a range of different catalysts, and from metal nanostructures to carbon-based materials and two-dimensional material-based hybrids. For the format, generation, we are focusing on the metal nanostructure-based materials, and for carbon, monoxide generation. Except, in addition to the metal nanostructures, we are also, developing the heterogeneous and homogeneous and hybrid catalyst, single atom catalyst, and heteroatom doped carbons. And I will hand over to Dr. Sixuan Guo, and she will present some samples from our center.
Good afternoon, everyone. So now I will show you some of our best performing catalysts for the generation of formate and CO, and compare them with those in the literature. In determining, when we determine the performance of a new catalyst, 3 key parameters are usually used. They are Faraday efficiency, overpotential, and product partial current density. These parameters are important because they determine the energy and electron costs for the large-scale process. So for the formate generating catalyst, our best performing ones are tin and bismuth based. The porous tin oxide nanosheet on carbon supported on carbon cloth achieves a Faraday efficiency for formate of 89%, with a very high partial current density of 50 milliampere per centimeter square. However, it requires a high overpotential. The tin sulfide derived tin supported on reduced graphene oxide achieves a similar selectivity at a moderate overpotential, but the current density is a bit lower. The porous bismuth nanosheets can selectively produce formate at a reasonably high partial current density. However, it also requires a high overpotential. While the bismuth nanowires ground on a porous copper form can selectively reduce CO2 to formate at a moderate overpotential, although the partial current density is not the highest. In the literature, although the palladium nanoparticles can selectively generate formate at a very low overpotential of 0.1 volt, this catalyst is not only expensive, but also prone to CO poisoning. And this limits its potential practical applications. The tin sulfide coated on gold needles combines the advantages of field-induced reagent concentration of gold needles and sulfur modulated tin, and selectively produce formate at a moderate overpotential with a partial current density as high as 55 milliampere per centimeter square. As for the bismuth-based catalyst, the nanoflakes deposited on a copper film has almost 100% selectivity for formate at a moderate overpotential. However, the current density is very low. While for the bismuth nanodendrites on a carbon paper requires a very high overpotential to reach a certain a reasonable rate. So now I'll show you some highlights of our bismuth nanowire catalyst. So in this project, we use a porous copper form as the 3D template to enhance the surface area. And bismuth-coated copper form was generated by a galvanic replacement method, and then calcinated in air to partially oxidize bismuth to bismuth oxide. During electrochemical reduction, bismuth oxide layer is reduced and forms twisted nanowires with crystal lattice dislocations, as you can see from the images. In the 2 figures to the right, you can see that formate Faraday efficiency of higher than 93% can be maintained across a potential range of 300 millivolts. And these high activities are attributed to the grain boundaries and large catalytic surface area. For CO generating catalysts, we have synthesized nitrogen-doped porous carbon from biomass and amorphous molybdenum sulfide supported on PEI modified reduced graphene oxide. Both have about 85% of selectivity for CO at moderate to high overpotential. It's worth mentioning that when this molybdenum sulfide composite is deposited on a porous carbon cloth, partial current density as high as 55 milliampere per centimeter square can be achieved. And this was the champion at the time. Silver chloride derived silver nanosheets has high selectivity for CO at a low overpotential. However, the current density is very low. Two molecular catalysts were also used. One is mixed with graphene oxide to form a hydrogel, while the other one uses an iron liquid as a co-catalyst. Both have high selectivity for CO at moderate overpotential, but the current densities are low. Our amine modified ultra-small gold nanoparticles supported on reduced graphene oxide has a 75% selectivity for CO at moderate overpotential. The mass activity is as high as 257 ampere per gram of gold. And in the literature, as you can see from the bottom table, gold-based catalysts are the best for CO formation. And the benchmark is set by the 8 nanometer gold iron Kocher nanoparticles, which is the second entry in the table. It has a very high selectivity of 97.6% for CO at a low overpotential. However, its mass activity of 48.2 ampere per gram is a lot lower than our gold catalyst. Due to the high cost of gold, it's crucial to enhance its utilization efficiency while maintaining the high activity for these large-scale applications. And in this project, we synthesize gold nanoparticles the size of about 2.4 nanometers, supported on reduced graphene oxide, and then modified these nanoparticles with different types of amine. In the middle figures to the right, you can see that linear amine modification leads to the highest selectivity. And this is because it forms hydrophobic environment around these active sites, which greatly suppresses the competing HER. Moreover, the ratio of carbon monoxide over hydrogen in the product can be tuned by the modification of different type of amine. And the results I reported here were all obtained from H-type cells. Due to the low solubility of CO2 in aqueous solutions under ambient conditions, the performance is limited by the mass transport of CO2 to the electrode surface. In order to overcome this limitation, a flow cell with a gas diffusion electrode can be used. I'll now pass it over to Claudia, who will show you what we have been doing in this area. Thank you.
Good afternoon, everyone. Our group work also toward the development of the electrochemical cell for CO2 reduction. On this video, you can see the reactor which operates with the 10 centimeter square gas diffusion electrode. this anode and the cathode compartment is separated with the membrane, which means this reactor is suitable for the gas and the liquid products. We tested this cell with a silver gas diffusion electrode, and we got a high Faradaic efficiency. However, we notice some loss of the current due to the scaling up from 1 centimeter to 10 centimeter square surface area, and the loss was around 30%, which actually brought us to try to different approach with making an assembly of the small cell in the stack design. Next slide, please. On this photograph, you can see 2 small cells in this assembly. And this kind of stack can work in the series or in parallel electrical connection. The preliminary testing were actually very optimistic. We haven't seen much current losses, which was a good start. On the end, I would like to also say that we have here the capability of 3D printing, which means we can actually print in plastic or in metal every part for this cell, including a metal scaffold for the electrode. For the collaboration, please contact Professor Doug McFarlane or Professor Gordon Wallace. And now I would like to ask Sam to share with us a live image of our devices. And I would like to ask Professor Doug McFarlane for concluding remarks. Thank you.
So thank you, Claudia. And here we have Sam, live, so to speak, showing you what these cells, these multi-element cells look like. And I guess his hand gives you a nice idea of the scale and all the little gas fittings and so on. Thank you all, in fact, Claudia, Sichuan, and Keyun for your lovely presentations. And of course, there's some great work here too over quite a few years. And I think this has certainly got some future. I think the economic data that Keyun presented at the beginning is quite compelling in regard to, for example, the potential for CO among the simplest of products to be economically quite viable in terms of the price compared to existing CO production. So thank you all, and thank you for joining us, everybody. And this is now open for questions and further discussion, and we can try to sort of show you more about these cells if there's anything more you'd like to ask about them or see in them or on them.
Doug, I might just get the ball rolling a little bit with a question for yourself. I mean, so we've seen all those potential products through CO2 reduction. And is there a standout product that really makes a big difference in terms of that's the one to chase, or is CO and format the actual ones that can give some commercial opportunity in the shorter term?
CO and syngas has always struck me as being one of the most obvious, and Keyun made this point very clearly, most obvious, because it's achieved at relatively low overpotential, so relatively high energy efficiency, as well as selectivity. And the syngas is almost completely selective in the sense that it's a mixture of hydrogen and carbon monoxide, which is very useful. So that's an obvious one. And of course, one of the features perhaps that we didn't talk to very much about is that that technology such as this can be implemented at quite a small distributed, i.e. localized scale. In other words, in a plant, could be quite a relatively small scale plant that needs CO or syngas. This can be produced effectively locally for that particular use, as long as there is a supply of CO2. So it will be, I think, very much a horses for courses situation. The application might spring up from some place where that particular feature has high value.
Thanks.
I don't know whether Paul Barrett is still with us, but I'd love to hear what Paul thinks about that comment. I know that that was a key feature of some of the aquahydric strategy in the early days, was small scale distributed.
Hey, Doug and Gordon, good to see you. Sorry, I got my camera off. I'm surrounded by school kids at the moment, so I'll keep the camera off. The nature of these Zoom offices these days. Yeah, great talk. Really like that economics slide, and good to see the delta, I think, between on the carbon monoxide side, between its, relatively high price and relatively low, power input needed. So that could well be one to go after. Yeah, I've also always found syngas to be a really interesting one because it's such a useful kind of building block chemical, and you had that nice chart that showed from Fischer Tropsch to making methanol. So lots in the syngas. I didn't quite get your question, Doug. Merits of going small or going big? Was that
well, going distributed, as in localized production for localized needs?
Yeah, I think it depends, right? So if I look at those big markets like that you're trying to get into with those carbon replacements, whether methanol, formate, they're all built on kind of a big industrial scale today, kind of big petrochem plants. So there's not, this is an assumption, I'd have to look at it more. I would assume there's not really a good decentralized infrastructure today. But if you are making something for on site, close that supply chain loop, that could be interesting. But I've always found the economics of a smaller plant not great compared to a big one because of the balance system costs. So I think it depends on the opportunity and ultimately the scale.
Yeah.
And certainly with the hydrogen electrolyzers, to really get into kind of a decent economic zone, you need it to be above kind of a megawatt in size. So, to visualize that, that's probably a shipping container sized electrolyzer is about a megawatt, depending on the technology. But that just gives you a sense of scale. That's where the economics started to plateau.
Good. Thanks, Paul.
Doug, it's Charlie here. Presumably you need a high concentration source of carbon dioxide as your feedstock into this process?
Look, that's certainly what we're doing. It's a pure CO2 supply that we use at a larger scale, of course. And there, through carbon capture, whether it's a cement plant or even a power station or whatever, that kind of concentration and purity is sort of a feature of the carbon capture technology. I guess I should also mention the gas cleanup, so to speak. Natural gas cleanup stage is usually quite a major source of CO2 as well, although not usually in very convenient places. If you're sort of thinking about the idea of running it directly from the atmosphere, that's a challenging but an interesting prospect. It's probably likely that some sort of pre-concentration of the CO2 is going to be necessary before that's going to be viable. The problem is that you immediately, if you don't have much CO2 around during the electrochemistry, then you just get a lot of hydrogen. Very hard to avoid that.
This is Ashley Roberts from Woodside. Was at Monash before, but I'm wondering, your catalysts are quite interesting, especially with the mixtures. And have you done a lot of work to see how they'll scale up? And also, can you control the reliability of those various formations as you start the scaling process?
Good question, Ashley. Certainly, we typically don't make these in very large quantities ourselves locally, or do very much about sort of investigating that aspect of it. But in terms of kind of how stable that formulation is in various respects, Sishuan, can you comment more on that?
Usually we test the catalyst for like 12 hours or more, and the stability is quite good. Yeah, it's just that in terms of this industrial scale, I think because like I have mentioned, the performance in H-type cell was limited by the solubility of CO2 in the aqueous solution. So I think the flow cell with the gas diffusion electrode is the way to go for industrial scale applications.
Yeah.
Yeah, and are you aware of the kind of new initiative there at Monash with the Woodside Energy Partnership about working with the carbon to products pathways, carbon utilization, and there's going to be an application, I think, for a hub concept.
Yep, we are very much so. We're sort of quite at least some of us who are online today are quite heavily dialed into that. Yes.
Yeah, I thought so. So yeah, that's good. These kind of things fit quite well. I think catalysts and how we can improve material performance and develop better catalysts, especially. So it seems quite fitting.
Good. Yeah. All right. So thank you everyone for joining in, and thank you from the team to for putting together such an entertaining expose of all of this, and the videos and the live demo from Sam. Very good. So thank you all, and we'll hopefully see you again at another ACES event like this sometime soon. Thank you.
Thank you. Bye-bye.
See ya.